So last lecture, we started looking into this infinite horizon alternative offers bargaining game. We will finish that today. So let me just, to remind, draw the game tree part of it. So two agents worked together, generated 1 unit of a good. And then the problem was how to split this 1 unit among themselves. The method that they would be using is, first, agent 1 makes a proposal on how much he should get, and hence how much agent 2 should get, which is a number between 0 and 1. So I will just write here, each action will represent the quantity that agent 1 would get. So once we know how much agent 1 would get, we already know how much agent 2 should get. So rather than writing x1 minus 1 minus x1, I will just write x1. Then player 2 takes an action. He or she can accept or reject the offer. If he accepts, the game ends. I'll write the payoffs later. If he rejects, then a new period starts. So this was period 1. Then a new period starts, period 2, which starts by agent 2 making an offer, again, which could be any number between 0 and 1. Again, by our offer, I mean he tells how much agent 1 should get. Okay? Hence, agent 2 gets 1 minus the offer that agent 2 made. So let's denote that with x2. Agent 1 then takes an action. He could accept or reject. If he rejects, well, if he accepts, the game ends. If he rejects, we start a new period. This time, agent 1 makes an offer, and so on. Okay? And the payoff says each agent prefers getting more to getting less, and getting it sooner to getting it later. Okay? So we said I will not get into the details of that, but agent I, we said, discounts future payoffs, future gains at the rate of delta I. So the payoffs we had was x1, 1 minus x1 here. x2 times delta 1. Agent 1 discounts future payoffs at the rate of delta 1. And agent 2 discounts them at the rate of delta 2. So that's if they agree on a division at period 2, a division where agent 1 gets x2 units and agent 2 gets 1 minus x2 units, their payoffs, the numbers assigned by the numeric representation is delta 1 times x2 for agent 1, delta 2 times 1 minus x2 for agent 2, and then we keep going on like that. So in general, when we're at period t, this is delta 1 to the power t minus 1 times x t, delta 2 to the power t minus 1, 1 minus x t, if this is t, okay? So that was the structure of the game. And as the game continues, so there's many infinite histories. The payoffs assigned to infinite histories are like t goes to infinity, okay? So we were analyzing this game. We said because this is an infinite horizon game, the length of terminal histories, there are terminal histories of length infinite. We can't use backward induction, okay? But then what you guys noticed was that actually the subgames, I'll first say it in mathematical terms, is isomorphic to the original game, okay? So I'll say it in more layman terms. Any subgame is identical to the original game, except possibly a renaming of the agents. Okay? So that's what we noticed, and that's a very strong tool that actually enables us to use to find subgame perfect Nash solutions of this game. Okay? So last lecture, we defined, well, so we don't even know whether a subgame perfect Nash solution exists or not. Wait, just a few more notation. We denoted with gamma sub I was the game, the alternating offers bargaining game, which started by an offer of agent I. So gamma 1, capital gamma 1, is the alternating offers bargaining game where agent 1 starts, where the game starts by agent 1 making an offer. Capital gamma 2 is the alternating offers bargaining game where the game starts where agent 2 making an offer. Okay? Again, we did not, so the game we're interested with, gamma 1, we're looking at the subgame perfect Nash solutions of this game. And the theorems that we have at hand, which is actually in this point, at this point there's only one, which says every finite perfect information game has at least one subgame perfect Nash solution. Well, this is a perfect information game, but it's not finite, so that theorem is of no use for this game. So we don't know whether the game has a subgame perfect Nash solution or not. We're looking for it. So what we do is we do a trick that we sometimes employ in mathematics and economics. We start by assuming that there is a subgame perfect Nash solution. Okay? So we start by saying, assume that this game has a subgame perfect Nash solution. By the way, if capital gamma 1 has a subgame perfect Nash solution because of the isomorphy, capital gamma 2 also has a subgame perfect Nash solution. All you do is just rename the agents. Okay? So we defined capital M 1, 1. I forgot which ones we defined, but what I'll do is I'll define the general. So for any ij in n, 1, 2, let's define capital Mij to be, I'll first write it in the form that we'll use in this lecture. Last lecture I talked about supremum, infimum. Quite a number of you didn't know about it. So I'll use maximums and minimums. But what I wonder is, how many of you looked up the definition of a supremum and infimum? One? Well, that's two. That's good. Okay? So don't expect everything from your instructors. You have to search for certain things yourself. That's what makes a good researcher. That's what makes a good student. Okay? So I can give you the definition, but you can open an analysis book. You can go to web, enter sup inf, and then find. And you don't expect everything from us. But let's go back. Okay? I'm glad that at least 2 people did look for it. That makes me happy. So we define this as the maximum of ui of S, where S is a subgame perfect Nash solution, so it's a strategy profile of the game gamma J. The game where agent J, the game in which starts with an offer by agent J. Okay? So small Mij is equal to the minimum of the same thing. Okay? So far, so good? So, again, if I was doing a strictly mathematical approach, if I was taking a strictly mathematical approach, I wouldn't write max here. I would write sup here. I wouldn't write a min here. I would write an inf here. But for our purpose, we'll work with the max and min. Okay? But again, those, you should look into why should I written sup here, the supremum, and the infimum here? You should ask yourself, why is this the proper, correct way of doing things rather than taking the max and the min? Okay? But that's what we had. Okay? So actually, that's roughly where we stopped last lecture. Okay? So now, we said, let's look at this game, analyze the behavior of player 2. So I'm looking at the sub-game following an offer of agent 1. Okay? So what could agent 2 do at a sub-game perfect Nash solution? Okay? So at any sub-game perfect Nash solution, if player 2 rejects the offer, he or she knows that they will be playing a game which is identical to the original game, except for the renaming of agents 1 and 2. Okay? And at any subgame perfect Nash solution, the maximum payoff that he can get at this game is the maximum payoff that agent 2 can get at this game is going to be, so it's going to be M, capital M, because we're talking about maximum. We're talking about the payoff of agent 2. And this is the game, the subgame of this game, which starts with an offer by player 2. So M, 2, 2. Okay? But of course, you see, this is the original game. They have the same preferences, but all the payoffs of player 2 are, you take this game, multiply all the payoffs of player 2 by delta 2. Okay? That's how you obtain this game, the numeric representation of this game. Okay? So when he's looking at this point, when he says, if I reject what I can expect the maximum payoff from this point on view is going to be delta 2 M, capital M, 2, 2. Right? Yes, sir.
Isn't that included when we are calculating M22?
Which one is included?
Delta 2. I mean, when we are calculating M22, we are looking at these UI.
Okay. So let me draw the game gamma 2. What is the payoff that I put here? X1, 1 minus X1. Well, gamma 2, when I look at it, gamma 2, so when I say this game is isomorphic, is equivalent to this game, up to the renaming, they have the same preferences, okay? But the numerical representations that we use here and here are different, okay? So to make the comparison, I have to have the same numerical representation. So how do I get the same numerical representation? Rather than using these numbers as a numerical representation of the preferences, I'll use this. That's one way to look at it. The other way to look at it is, if they're playing this game, if that's where the game starts, this is like period 1, then the payoffs would be 1 minus x2, x2. Okay? So when he says, if I reject tomorrow, I expect to gain at most this much. Gaining this much tomorrow is worth how much today? Delta 2 times M22. Okay? So you can use two perspectives, the game tomorrow, or just that's the game. But even though they have the same preference relations, the numeric representations that is here and that is here, okay, when I have the delta 2s okay, are different. So what do I have to do? Adjust for the numeric representations. Okay? Two approaches, no matter what, it says that they should have a delta 2 here. Okay. So, what does that say? Well, the strategy of player 2 should be a best response to the strategies of player 1. And if he rejects, that's the most he can get. So, based on this, the strategy of player 2 should be such that accept any offer which is bigger than or equal to this. Okay? Right? Okay? Sorry? And, well, reject anything less than that? I'm not sure about that. Because, you see,
it's not guaranteed you'll get the maximum.
Exactly. It's not guaranteed I'll get the maximum. You know, if that's true for the minimum, if any offer which will guarantee him delta 2 times small m22, he would reject. But in between, we don't exactly know because we don't know what's going to happen. It will depend on the strategy profile. If it was, okay, so we'll look at the, so that was the other question that I asked. Well, not question. That was the other thing that I asked you to do, the other request that I made. How many of you thought about the finite version of this game? Okay, the usual suspects, but okay. You should look into these things. Huh? You see, it's, anyhow. Okay, so what does that mean? Well, if agent 2 is going to accept any offer which is greater than delta 2 times m22, okay, what is the minimum payoff that player 1 can guarantee himself? Exactly. So player 1 can guarantee himself 1 minus delta 2 m22, any payoff, greater than or equal. Well, if it's equal, player 2 is indifferent between accepting and rejecting. So we could consider a strategy where player 2 rejects. So which means that player 1, by saying that I ask for this much, okay, can guarantee himself at least this much payoff. What does that mean? Sorry? No, exactly. M11 is greater or equal to 1 minus altitude. Okay? So far, so good? So that's one inequality we have. Well, what else? Now let's go back to what your friend roughly suggested. Player 2 will reject if, you know, any offer which gives him less than delta 2 m22, because, you know, once he rejects, tomorrow he can guarantee himself small m22. The value of small m22 tomorrow is delta 2 times small m22 today. Okay? Which means player 1 can guarantee himself at most 1 minus 7. So that's another thing we have. Okay? So far, so good? So what we have is, well, by definition, the minimum is always less than or equal to the maximum. Okay? So far, so good? Any questions? Oh. Thank you. Okay, any questions? We can write Similar conditions for small m22 and small m11, right? Well, the games are symmetric, so all we have to do is, replace all the ones with twos. Okay? Okay? So, what can we do now? Well, the rest is a little bit algebra. For example, if I use this and this and these, so, well, what I want is I want to have an system of equations, inequalities, which involves capital M11, for example. So using those, I have to be careful. I keep making arithmetic mistakes. I have to be careful about the. So let me write that step by step. So we have 1 minus delta 1 capital M11 less than or equal to M22, which implies 1 minus M22 less than or equal to, well, divided by delta 1. Remember, we took delta 1 greater than 0. Whenever you're doing division, be careful not to divide by 0. So M11. Okay? I hope I did not make any mistakes there. Okay? Move that here, move that there. Yep. So this together with this will give me 1 minus M22 divided by delta 1 less than or equal to 1 minus delta 2 M22, which would imply 1 minus M22 less than or equal to delta 1 minus delta 1 times delta 2 M22, which would imply 1 minus delta 1 divided by 1 minus delta 1 times delta 2 less than or equal to M22. Right? I hope I did not make any arithmetic mistakes. I keep making sign mistakes, so I have to be careful. Moved it here, became positive. So factored it out. So 1 minus, yeah. Okay? So far, so good? So now I know something about M22, which also implies that I know something about M11, right? Now let's try to get something about capital M22. Let me erase this part. So what do we have? I'm looking for capital M22. So I'll use this. Okay. Capital M22 is less than or equal to. So I'm going to try use this and get rid of M11 and have something which only involves M22. M22 is less than or equal to 1 minus delta 1 M11. So it implies that M11 is less than or equal to 1 minus M22 divided by delta 1. Again, I can do the division, no problem. So this, together with this, implies 1 minus delta 2 M22 less than or equal to 1 minus M22 divided by delta 1. So that implies delta 1, delta 1, delta 2, M22 less than or equal to 1 minus M22. And that implies that M22 is less than or equal to 1 minus delta 1 divided by 1 minus delta 1, delta 2. So far, so good? Okay. So just simple algebra. So I'm trying to get rid of, I'm trying to get inequalities which only involves one of these MIJs. Okay. So what do we have? We have this, and we have that. So let me write those together. 1 minus delta 1, 1 minus delta 1, delta 2 less than or equal to M22 less than or equal to capital M22. That already always holds. 1 minus delta 1, 1 minus delta 1, delta 2. So what does that imply? They're equal. And they're equal to 1 minus delta 1 over 1 minus delta 1 times delta 2. Okay? So far, so good? Any questions?
We have also to find M11.
Yeah. Well, so what do you think? So what do you think this is equal to?
It will be 1 minus delta. I think delta, like M11, small and capital, they are the important thing because here we have
What was the important thing?
to determine the payoff of the subgame perfectness because here we have player 1 as the first mover, and he will propose he will offer 1 minus M11, and the player 2 will accept.
So how do we know that?
We know that because, for example, if you go on the next stage, we know that player 2, the maximum he can get is 1 minus delta, like the expression.
Wait a minute. The maximum, so I raise the game. So player 1 moves, x1, then player 2 accepts or rejects, and then we go into period 2. Player 2 makes a counteroffer. Okay.
X1 will be
So in this game, if we think about this as gamma 2, the maximum payoff player 2 can make is M22. So when we translate that to this game, it's going to be delta 2, M22. So what's the conclusion that you get from there?
the payoff will be 1 minus delta 1.
Whose payoff?
Payoff of player 1 will be 1 minus delta 2 over 1 minus delta 1 delta 2
So the payoff of player 1 is going to be 1 minus delta 2 over
1 minus delta 1 delta 2. No, the whole expression.
this thing. So let me write it maybe like this. You mean this?
1 minus delta 1
So 1 minus
delta 2.
delta 2
1 minus delta 1
over or just times 1 minus delta 1.
over 1 minus delta 1 delta 2.
1 minus delta 1 delta 2. That's, so how do we know that this is the case?
Because the maximum on the minimum that player 2 can get in the next round when he's the proposer is the expression of the premise.
Uh-huh.
And if we offer less than that,
He will reject.
exactly that amount.
He will accept.
For that amount, we have to discount the delta 2.
Uh-huh.
And the rest we keep it for ourselves. That's why we have 1 minus.
Okay, so the rest you will keep for your self. Well, let's see. So your friend is using the fact that so when he rejects, he will exactly accept, he will exactly get this amount. Player 2 will exactly get, because, player 2 will exactly get once player 2 rejects. If they're playing a subgame perfectness solution, in this subgame, player 2 will exactly get this amount, okay? Which means that he will accept any offer which is greater than this times delta 2. So let me write that. He will accept anything delta 2. So if they're playing a subgame perfect Nash solution. So we're saying that we have determined what the actions under a subgame perfect Nash solution of every subgame following this history is. What we're trying to do is we're trying to determine how they will behave in this part. Okay? So if they play according to the subgame perfect Nash solution, which we assume that exists, which we don't know whether it exists or not yet, the payoff, the maximum payoff that player 2 can get is going to be this. So translated to this period, it becomes delta 2 this. Okay? So which means that if there is a subgame perfect Nash solution, player 2 should accept any offer which gives him at this much and reject any offer that gives him or her less than that. And if they're equal, he will or reject.
Should accept.
Why?
Because if you reject, then we cannot have the subgame perfect Nash.
Well, so how do you know that it gives the same payoff if you're indifferent between accepting and rejecting?
Because if you reject, then we'll go on the second stage.
And that's the payoff.
Offer something to player 1 that will keep player 1 different as well.
Well,
If that goes on,
we don't know what's happening there. So you see, the key here, when you're doing this analysis, okay, this is what we have assumed that player 2 will get if the game continues. Okay? So he's indifferent. Okay? We've already made an assumption on how they will behave. They will behave in a subgame perfect Nash manner. So I don't know what is going to be offering here. I don't know what player 1 will do, whether accept or not. But whatever they do, okay, the maximum payoff that player 2 can get and the minimum payoff, well, the exact payoff at any subgame perfect Nash solution that player 2 can get is this. Which means that if player 1 exactly offers this much, okay, he's indifferent between accepting and rejecting. Okay? That's one thing. So if he makes an offer of delta 2 times 1 minus delta 1 over 1 minus delta 1 delta 2. How do I know that accepting is a best response? Yep.
we have 2 players and they are economic agents. And since, for example, player 2 is indifferent between accepting and rejecting, and if he chooses to reject, so will player 1 too in the next stage when he's the proposer.
How do I know? Maybe they're doing so. If you remember the game that we studied at the beginning of last lecture, sometimes they accepted, sometimes they said stop, continue, stop, continue. So maybe he behaves one way. So maybe there is more than one subgame perfect Nash solution, okay? Which could be accepting always and accepting sometimes and rejecting sometimes. Intuition suggests that it should be, but we need more than intuition. Wait a minute, your friend had a comment. By the way, how much time do we have? Ooh. What do you mean by plays their maximum?
Like if they both play this amount, like
So by the way, when you say they always play this,
not always. They will eventually find these numbers. So can they accept that?
so what does eventually mean?
When we are trying to find the offers that for 2 agents, the best ones, right?
Well, what we're trying to do is if we're trying to find, we don't know whether a subgame perfect Nash solution exists or not. We assume that it exists. So what we're trying to do is usually when we do things like this, we don't know whether something exists or not. We assume that it exists. And then if it existed, we ask ourselves, if it existed, what would it look like? Okay? What kind of a property would it satisfy? Okay? So that's what we're trying to do. So if it existed, I don't know what it looks like, but the maximum payoff that player 2 would get at this part is this payoff. So by that, I know that he's going to reject any offer which gives him less than the maximum and the minimum payoff. The payoff that he's going to get under any subgame perfect Nash solution, whether it's single or infinitely many or 5 or 6, I don't know, they will all yield the same payoff, this, okay? Okay? So, which means that he would reject any offer which gives him less than this, accept any offer which will give more than this, will be indifferent between any offer accepting and rejecting which gives him exactly this. Let's give you a fraction.
Since I understand, I think that he would accept because there's no reason for him to reject.
So, you see, you should be careful not mixing intuition with mathematics, with techniques, okay? Yes, that's what my intuition says too, okay? But I have to prove it. Mathematics says that he's indifferent between them. If he's indifferent, he could accept as well as reject. If I had drawn you a game like this, player 1 takes an action, a simple game, left, right. His payoff is 1, or let me call A, R. Would you say that given this payoff structure, player 1 will definitely play A? Would you say that? No, then why are you saying that he'll definitely play A there? Yeah.
For example, if you offer him the payoff on the right and he rejects, so I, as player 1, should offer him something more for him to accept.
Why?
Because if we go on in the next stage, I'll get a smaller payoff than offering like a slightly bigger than this.
Okay, so actually,
And also my minimum payoff would be smaller than what I have there, 1 minus delta 1 over 1 minus the payoff.
okay,
and 1.
so maybe we should look into those things, okay? So what is you see, we should look into those payoffs, okay? So now we're getting more mathematical, okay? So if he rejects, we kept looking at the maximum payoff of player 2. Now we should look at the maximum payoffs of player 1 also maybe, okay? Which now we're getting more technical. Question or comment?
So he doesn't care about what player 1 gets.
He doesn't care exactly.
Yeah, but the offer, like player 1 cares for his payoff, so I can just offer him how much you're going to reject, I'll offer something more. So you accept, I will not get less this second payoff because I know that as soon as I propose her, I'll get less because the pie also shrinks.
Then he's suggesting that delta 2 times 1 minus delta 1 over 1 minus delta 1 times delta 2 plus epsilon should be the same.
Yeah, but if that
Okay.
is the case,
But that's not a subgame perfect.
yes, that's why
So-
you should accept.
So the moral of the story could be there's no
No,
subgame perfect Nash solution.
We saw this in 204 because there is a subgame.
There is a damn, the 204 spoiled all the player. Well, maybe in 204 it exists, but for 439 it doesn't. Things change. You give him a candy. Okay. Well, there's always ways to modify the game, but unfortunately, this is the game that we're analyzing. Okay. But you see, the thing is, first of all, you should see that he's indifferent. So just by looking at this, when player 1 says, I'll give you this much, okay, take the rest for myself, then player 2 is indifferent between accepting and rejecting, okay? So I can't just say that, well, he will accept because, you know, he's a nice guy, he will think about future. What this implies, let me go back to one of the games. Well, I'll probably will not be able to draw the game that we did before, but let's look at this game. Simple game. Okay, I don't care about the payoffs of the rest. So if we were using backward induction to solve this game, what would you do? Look at two cases. Look at the case where player 2 plays L here. Look at the case where player 2 plays R here. Okay? So this game could have two subgame perfect Nash solutions where player 2 plays L in one of them and player 2 plays in R of them. Or maybe when he plays L, it doesn't lead to a subgame perfect Nash solution. Only R does. Okay? Okay? So here, player 2 could be playing A, could be playing R, but maybe playing R does not yield the best response for player 1 here. Hence, that could not be a part of a subgame perfect Nash solution. But playing A would, which is what your friend had an idea. So here, player 2 is indifferent between them. So what we mean is that we should analyze the case where we have player 2 plays R, analyze the case where player 2 plays A. If for both of them, player 1 has the best response, it means that we could have more than one, I'll say, type of subgame perfect Nash solutions, okay? Because we don't really know how many there are yet, okay? Okay? If only one of them does, then we will say there is one type of subgame perfect Nash solution. If neither does, then we will say this game has no subgame perfect Nash solution. Okay? Actually, if you had solved the finite version of it, you would have run into the same problem. In the finite version, it's easier to see it, so I wish you had solved the finite version. Okay? In the finite version, the strategy, which is a part of a subgame perfect Nash solution, the strategy of player 1, which is a part of a subgame perfect Nash solution, player 2 is indifferent between two actions, even in the one-period version, is indifferent between accepting and rejecting. But one of them leads to a subgame perfect Nash solution. The other one does not. So I strongly recommend try the finite version too. Start with the simple one period. Player 1 makes an offer, player 2 accepts or rejects, game ends. Okay? Then look at the 2 period. Player 1 makes an offer, player 2 accepts or rejects. Okay? And look at those and see what you get. Okay? Yep.
Each player, when he is the proposer, he will keep M22 for himself, the share of the pie that is, and the other
Well,
player will always
well, first of all, that's not a, is that a, will always accept. So what do you mean by always accept?
accept
Again.
when he's offered like an amount that he is indifferent between accepting or
Okay.
rejection, going to have it.
Okay, so again, we're talking about strategies. We're not talking about action. So when you say always accept, it's like the action that player takes during the subgame perfect Nash play, okay? Which is different than the strategy. So if I'm describing a strategy of player, for example, 2, I would say he accepts when he's offered at least this much and rejects if it's offered less than this, okay? And then when we're writing the strategy of player 1, for example, not in this period, well, I'm panicking because we have only a couple of minutes. So actually, well, we'll finish this thing next lecture. When I rush, I think, things start getting messing up. I did not do what I always tell you to do before you start analyzing the game. What is the strategy set of the players here? Okay. You don't always have to write it, but you should always think about it. Even if you don't have a mathematical structure which gives the strategy set, you should have, at least in your mind, you should have thought about what it looks like. Okay. So S1, it's a sequence. No, you see, you try. It's okay to be wrong from your mistakes. You started something. Some of your friends will notice some mistakes, and they'll try to fix it, and we'll be at a better position, hopefully.
Maybe we can put two things in the sequence.
Mm-hmm.
And one of them will be accept rejection, one of them will be like 0, 1.
Okay. So maybe two things in the sequence. So what does the strategy set of players look like?
We have also like the first node.
Uh-huh. Well,
Express that as a secret because it will be also only
Oh. Okay. Well, your friend has. As a tuple, a pair. Is it still a sequence of pairs or just a pair? Pair of sequences. So.
First sequence will be a sequence of numbers between 0 and 1.
Okay, so let me call them A. It belongs for player 1, so let's put 1. T for period, right? So the sequence probably corresponds to. So several of you had sequences in mind. So I'm guessing that the sequence is about the period, right? Something that tells us what they do in the first period, the second period, the third period. That's why I put T there. Is that what you had in mind? Or something different? Okay, well, do you want to write it yourself here? Come on, give it a try. Catch. Oops. I have more markers here. Come, sorry, my fault. Okay, well, let's give your friend a chance and then we'll stop. We'll finish it next lecture. I'm sorry, we're going over time for just 1 minute.
A1 table element of
1.
1, roll T 1, 3.
Okay, for all odd, okay.
Odd periods,
Uh-huh.
because those are the periods he makes.
Okay, good.
And these will be functions.
Mm-hmm.
Functions from an offer made to accepting or rejecting,
Uh-huh.
and this will be for even periods.
Okay, thank you. So far, so good? So far, so good? Everybody agree? Can we call it a day?
Can't we do this with a single sequence too?
I don't know. Think about it. Well, it's close, but it ain't it. We got closer, but it's not this. So think about it. Next lecture. What's wrong? Well, I don't want to take up your friend's time. We can talk about it. Okay.